Welcome to Lesson 3. We are going to talk about honest assessment. The out-of-sample evaluation is an assessment tier which complements the statistical assessment tier discussed in Lesson 2. But first of all, why do we need such a complement to the inferential statistics? Here we are going to discuss that. Inferential statistics tools have been tailored in the second half of the 18th century for experimental studies, namely for clinical research applications. Trading system design, though, has little to do with experimental studies. It can be assimilated to an observational study. Well, let's see first what experimental studies are about. To put it in a nutshell, experimental studies are about assessing one predictor called treatment that in the clinical research context may be a drug. The response of the people who are treated with said drug is then compared with that of the people treated with a placebo. Hence, we have one predictor only, which is defined a priori. There are no choices about it. That is definitely the case where inferential statistics fully applies, with no need for adjustments. A common practice of researchers, though, is to complicate a bit that scheme in order to encompass more predictors, more drugs in the experiment. They deem feasible that any of these predictors may be relevant, and then they include all of them. After that the experiment responses are collected, they start an exploratory analysis, reviewing the collected data to figure out whether one predictor is better than the others, or grouping predictors. That is called post-hoc analysis. That marks a slight departure from what we presented in the previous slide, where there was no exploratory analysis at all, and all was defined a priori. With the post-hoc analysis schematized here, the confidence intervals for the predictors would need some adjustments in order to cope with the so-called experiment-wise error time. This exploratory character is common to the observational studies entailed in the trading system design. The model fitting, in fact, chooses among the predictors. See Lesson 1 to these regards. These observational studies need adjustments too in order to avoid overfitting and confidence limits related issues. These adjustments, though, here do not come in the form of mathematical technicalities, but in the form of an additional test called OOS, which stands for Auto-Sample Test. The auto-sample test then complements the statistical assessment phase, and it is expressly provided for by the honest assessment practice. Let's try to summarize all that. We can say that we have a first assessment step which entails inferential statistics that is necessary but not sufficient on the ground of our previous considerations. This assessment step is then complemented by a second step, which entails the auto-sample test. None of these two steps alone is sufficient. They need to be carried out in conjunction for the overall assessment to be reliable. Let's see in details what the honest assessment provision is to these regards. We are required to assess a system on the auto-sample, that is a sample other than the training sample, which in turn is the sample used to build the predictive model. The performance reports must refer to the auto-sample only. MASASP even goes beyond that. Also, the statistical tests in MASASP are confined to the auto-sample, improving then their reliability. Well, let us see in details how this auto-sample works. The schema reported here represents an entry-level auto-sample analysis. This is a simplified view presented just for didactic purposes. Well, let us assume that we have 5 years of data available to design and assess our trading system. We split this dataset as follows. The first split covers the first 4 years and is used to build up the model. That is the so-called training set. It trains the model. The second split covers just the last year and is used to assess the model. That is the so-called auto-sample. That complies with the honest assessment provision mentioned so far. Nonetheless, it involves a couple of shortcomings. The first shortcoming is the limitedness of the auto-sample. It is confined just to the 20% of the overall dataset, which means 1 year only in this example. The second shortcoming is that the auto-sample is placed right at the end of the observation period, and then it might be biased. It is not representative of the whole history of the financial issue involved, and if the last year differs from the past years in terms of trending patterns, that might undermine the reliability of the assessment. Eventually, we come to the refined auto-sample analysis scheme adopted by MASASP that iterates a few times the splitting depicted before, once for each year of data. Let's see how it works. The track record related to year X refers to a model built on all years but X. Year X is the out-of-sample which delivers the track record for year X, and so on. Each year is then utilized as out-of-sample. That makes possible to overcome the shortcomings mentioned in the previous slide. This way, we wind up having a track record which doesn't strictly refer to a single model, but to a collection of year-specific models. Let me say that these models are siblings in that they are very similar to each other, and this similarity stems from three factors. The predictive modeling technique involved, the big historical depth, which involves as many as 12 years or even more, the model stability analysis, a refinement addressed in the next video. Let's see a real-life example regarding the short strategy of gold. Here is the outcome of the test component. That provides a basic track record that entails the details of each trade. Now you know that the trades reported here refer to the out-of-samples only. The smart thing in this wrapper is that the track records of different out-of-samples are gathered into this single record. Let's have a look at the columns in this record. The column points means the trade return in basis points. The column SZ means size. The figure highlighted in the orange circle is the position size of the trade. Finally, the Y-hat column, the yellow one, reports the voting of the base learners according to what has been presented in lesson 1. Here, Y-hat equals 2, then the position size is 0.5 because just 2 of the 3 base learners voted for going to the market. If we had had 3 votes here, position size would have been 1. This report excerpt shows the section related to Y-hat equals 3, where all base learners voted for the market. You can see that profits here are higher, as well as the percentage of winning trades. Well, that's all for the time being. Thanks for watching, and see you at lesson 3, part B, to tackle the model stability issue.